One of the tools for studying function of several variables is the partial derivatives. Partial derivatives. So we can imagine if having a function of two variables, okay. So if you remember derivative of function of one variable, so let's first give a reminder of the derivative. So it's change of quantity relatively to the variable, the change of the variable. So we defined f prime of x, 0 was the limit, okay, of f, if you remember, f x plus x0 plus h minus fx0, okay, or even at x without the index, just keep it general. We defined like that the variation, so it allowed us to remember to identify the slope at the point, and it was helpful for graphing the function at the end, okay. So here it is, h as h approaches 0. So this was the derivative of f at x, okay. So it expresses how fast f is changing when x is changing. So it's an instantaneous change, okay, of f. Okay, so for now, if I have a function of fxy, two variables, so I would like to measure something like that. But here the problem is I'm having two variables. So we can say, why not fix one of them and see how the f is changing? Why not? So we can then form the ratio, these limits. So I will change x while I maintain y, the second variable, unchanged. So I will estimate, so compute these limits, which gives me an information. Still, it gives me an information. Okay, so it's an instantaneous change of f while for y fixed. Okay. Okay, and this quantity we denoted f index x here, symbol x, at xy. Okay, we can also be interested in why not considering this time x fixed and y is changing. Okay, so I will put the index y at xy. This time I will have x fixed and y changing. Okay, so these are called partial derivative. This one is called partial derivative of f with respect of x, and here also this time with respect of y. Okay, so yes, this is our definition of partial derivative, and you see how, okay, it is yes, it measures something, it gives us something, information on f. So this is the definition. So let's do an example just to see how it works. Okay, so an example, what if I have fxy given by the formula exponential xy, okay, plus ln of x2 plus y. So I'm looking to compute the partial derivative with respect of x. So it's easy. So I see now. So I can use the differentiation tools we learned before. Y is fixed, so it's like a number, fixed number. So I focus on the variable x. I focus only on the variable x, and here y for me is a parameter like a constant. So this is I will need to use the general formula. So I will derive the first function, which is the exponential, so it remains the same, applied to the second function. Now the derivative of the second, so I will derive with respect of x the quantity xy, okay, general, plus derivative of second function, the same, chain rule. The derivative of ln is 1 over, applied to the second function, which is this quantity, times the derivative with respect of x of the second function. Okay, so which gives me axy. So here y is like a constant, so a factor derivative of x is 1, so it will be y plus 1 over x2 plus y, and here also derivative of y will be 0 because it is like a constant, and the derivative of 2x is 2x. Okay, so this is how we proceed. Okay, um, okay. Now let's give some remarks about notations. Okay, so similarly we define, of course, if you have a function of 3 variables, you can define fx, fy, and fz. Okay, similarly, so let's just, by guessing on the example, we can answer. Okay, so let's do the following example. With 3 variables. So here is my function. What if I have the function fx, y, z equal defined by x, y squared, z3. Okay, what is fx? So fx, partial derivative with respect of x. So I see here this term like a factor plays the role of factor. So I need to derive just the function x here, which gives me y2 z3 times 1. If I want fy, so I will have x and z3 like factors, and dy of y2, which gives me 2y, so we will have 2y x z3. If I want fz now, I can yes, focus, so xy2 will be a function, constant, and dz a factor, so of z3, and this time I will have 2z3 z2 xy2. Okay, now I use it here, different notation here. I didn't plot the point xyz because yes, there are several notation you can use. So let's write it here, notation. So we can fx, we can write it as fx. We can write it also fx at xy, specify the point. We can write this like that, df dx. Okay, those are the most notations you can have. Okay, now what about now? If you remark here through the examples, once we derive it, we found the partial derivatives. Then these partial derivatives are themselves functions of several variables. So we can also be interested in deriving these quantities with respect as function x, y, z. I can be interested in deriving fx, for example, with respect of x, with respect of y, with respect of z. Like that, we call them higher derivatives. Okay, higher order derivatives. So let's say keeping the notations. Why not? Yes, let's keep in the notations for higher derivatives. partial derivatives, okay, partial derivatives. So I can obtain, if I choose fx, I'm interested as function of 2, I derive it with x, I will denote it fxx, okay, or also second derivative of f with respect of x 2 times. So this is how we denote, okay. You may interested fx with respect of this y, so this one you denote it fxy, or you say it's I derive with respect of y the partial derivative with respect of x, and some we denote df dy dx, okay. So you see how the notations are different. Yes, fxy, and again we can imagine a third partial derivative. So if I take y, then I derive with z, so I will form fxy z, you see. So yes, so it's 3 times, so d3f dz dy dx. So you see the order is important. So as a remark, yes, about the order of differentiation. So is not important if your function is regular. Is not important if the function is regular. Function is regular. So you somewhere your function, you see it from its formula that you can take any partial derivative with respect of x, y, and z, they are continuous, etc. Then you can do that. What do we, the order what we mean? Then we will have then, for example, f x y z will be equal f z y x will be equal f x z y, etc. Okay, but is not important if the function is regular. So you need to check this. We don't insist here, we will deal only with functions very regular, because here yes, it requires more advanced results, okay. So this is mainly what I wanted to say. And yes, as an application, the functions appear as an application modeling, so they appear in the domain, they involve in the domain of partial differential equation, okay. We call it, yes, there is a domain mathematic called partial okay, domain in the domain of partial differential, so in the domain of PDE we call it, okay, partial differential equations. So they serve in modeling, they serve for modeling, for example, make equation in continuum mechanics, okay, modeling many phenomena like phenomena like continuum mechanic, I think it's like that, okay, mechanic, okay. So for example, we show that the temperature or the movement of sound, wave sounds, for example, the equation of waves is modeled by, we call it delta u equal du dt. Dt is the height, u is the height of the wave, I think, and delta u is called the Laplacian. Laplacian. Okay, it's defined by the second partial derivative. So everything here, of course, is related to studying many domain of mechanic physics domain. Okay, and then here the modelization that is suitable to such phenomena. Okay, so this is to give you an idea of one of the tools you may meet, and you see how it is a generalization, small generalization of the derivative definition of function of one variable, how we introduce it for several variable functions. And there are only other many more advanced tools that you can learn in second year calculus.